Hello everybody, I'm Akriti Kutyala and welcome back to my channel. We are starting a new series on RCC design, reinforced cement concrete, where you will not only learn about the manual design process, but also how to model it in Revit. This series is in collaboration with Novatr, a leading platform that helps civil engineers upgrade their skills with industry-focused courses on BIM, Revit and more. Through this series, you'll gain both theoretical knowledge and practical expertise to excel in the field. So stay tuned, it's going to be an exciting journey.
We'll be starting a new subject today called reinforced cement concrete using limit state method. The first topic which we'll be covering is design of beams. The reference books will be by Dr. B.C. Punya and by Dr. Birender Singh. The prerequisites for the course are the Indian standard for reinforced cement concrete, that is IS 456-2000. Make sure that you have a copy of it. In the previous lectures, we've covered 3 subjects, namely fluid mechanics, surveying, steel structure design and drawing. For fluid mechanics and surveying, we have an active membership plan called the Himalayan Birch. And for all the 3 subjects, we have an active membership plan called the Himalayan Oak. I urge you to subscribe to the membership plan. Now let's start with a numerical problem. Design a simply supported rectangular beam with the following data using LSM. LSM is limit state method. The clear span is 5 meters. Superimposed dead load is 20 kilonewton per meter. Live load is 15 kilonewton per meter. We've been advised to use M20 concrete and Fe415 steel. So we've been given Fe415, which means that the Fy, the yield stress of the steel is 415 Newton per mm square, and for M20 concrete, the characteristic strength of concrete is 20 Newton per mm square. In addition to that, we've been provided the live load, which is 15 kilonewton per meter, superimposed load, that is 20 kilonewton per meter, and clear span, which we denote by the letter capital L, is equal to 5 meters, and we'll be converting it into millimeters because we have to be very careful while designing about the units we are using. So that will be equal to 5,000 millimeters. Now, it is very important to write the given parts of the question because it makes it easier to start the steps. Now the next part will be nominal cover to meet durability requirements. In table 16 of IS 456-2000, we have been provided with various exposures, that is mild, moderate, severe, very severe, extreme, and we've been provided the value of nominal cover for each of these conditions because the question does not mention any exposure conditions, so we'll be assuming it to be mild. So in that case, the nominal cover should be greater than equal to 20 mm because it is very clearly written that the nominal concrete cover in mm not less than whatever the value we are choosing from here. So it is simply understood that nominal cover should be greater than equal to 20 mm if we are assuming mild exposure conditions. Now we'll be assuming the dimensions of the beam in step 1. So for the dimensions of the beam, we have the overall depth denoted by capital B, the width of the beam that is denoted by capital B, and the effective depth that is till the center of the tension reinforcement from the face of the top cover or top face of the beam. So this is denoted by small d. Generally, we assume this effective depth small d between span upon 10 to span upon 8. If we are provided with a clear span, we use clear span for this, and if we've been provided the effective span in the question, we use the effective span for this calculation. So now we have the effective depth will be equal to 5,000 upon 10 to 5,000 upon 8, which calculates to 500 mm to 625 mm. We'll be assuming a value of 510 mm. It simply means that the value which we assume for the effective depth should be between the two values which we have calculated. So 510 is well within the value which we have assumed. Now by this, the overall depth will be equal to the effective depth and the nominal cover. If you remember, we assumed in the previous question that previous part that the conditions are mild and our nominal cover should be greater than 20 mm. So we are assuming this nominal cover to be equal to 40 mm. So D, capital D calculates to be equal to 510 mm plus 40 mm, which is equal to 550 mm. The next part will be to assume or to calculate the value of B. We assume the width of the beam to be between D by 2 to 2/3 of D. D is the effective depth of the beam. So this calculates to be, I'm sorry, we take it to be the overall depth of the beam. So this calculates to be equal to 275 mm to 366.6 mm. So for our ease, we assume B equal to 300 mm. So now we have the value of the effective depth, the overall depth of the beam, and the width of the beam, which we wanted to determine in the first part. So moving on to the next step, we have the dimensions of the beam. Now we'll be calculating the effective span of the beam. For that, we'll refer to clause 22.2 of IS 456, which says that in simply supported beams or slabs, the effective span of a member that is not built integrally with its supports shall be taken as clear span plus effective depth, or the beam center to center of the supports, whichever is less. So we now need to calculate the center to center distance between the supports. For this, we need the width of the support. Since this is not provided to us in the question, we'll be assuming this value of width of support equal to 300 mm. Now we can calculate from clause 22.2a the L effective value. We calculate both these values and select the lesser one. This calculates to be 55,010 mm for L plus D, and for the center to center distance between the supports, it calculates to be 5300 mm. We have to use the lesser value from both these. So the lesser value is 5510. Pardon me, the lesser value is 5300 mm. So the L effective will be equal to 5300 mm. So in this step, we've calculated the effective span of the beam. Now moving on to the next step, we calculate the self-weight of the beam. To calculate the self-weight of the beam, we require the unit weight of concrete. So from clause 19.2.1, we have that for plain concrete and for reinforced concrete, the unit weight is equal to 24 kilonewton per meter cube and 25 kilonewton per meter cube respectively. Since we are considering it to be an RCC beam, so our unit weight for concrete will be equal to 25 kilonewton per meter cube, which is 25,000 Newton per meter cube. Now we have to calculate the self weight of the beam, which can be simply calculated by multiplying the overall depth, the breadth, the length, and the unit weight of concrete. But we will be calculating the self weight of the beam for per unit length. That is, the length which we'll be considering is 1 meter or 1000 mm, and gamma RCC is equal to 25,000 Newton per mm. Please notice that Newton per meter cube. Notice that we have to keep in mind the units. The value of D is 550 mm and the value of B is 300 mm. So we will have to convert either these two into meters or these two into millimeters. So converting these two into meters and dividing them by 1000, and it calculates to be equal to 4125 Newton per meter, which can be written as 4.125 kilonewton per meter for our ease. Now the next step will be designing the factored load. To compute the design factored load, we've been provided the live load equal to 15 kilonewton per meter, superimposed load as 20 kilonewton per meter, self weight as 4.125 kilonewton per meter. So the self weight and the superimposed dead load combined form the dead load on the beam, which is equal to 24.125 kilonewton per meter. Now the factor design load is equal to 1.5 times the sum of dead load and live load. So the total dead load is 24.125 kilonewton per meter and the live load given to us is 15 kilonewton per meter. We'll sum this and multiply it by 1.5 to factorize it, which computes equal to 58687.5 Newton per meter, and we can write it as 58.6875 kilonewton per meter. So this is our factorized design load. Now, the next step will be factor design bending moment. We know that for factor design bending moment, we require the value of factor design load, the effective length of the beam. So the factor design bending moment is WU L square by 8, where L will be L effective. We've calculated the value of WU and L effective in the previous question, so substituting them, we obtain MU equal to 206066.4844 Newton per meter. Please keep in mind that we are using the Newton and meter values for the corresponding values here. We cannot use this L effective to be 5300 mm because the WU is given to us in Newton per meter. So keep in mind the units and then only substitute them in the question or in the formula. So finally, our design factor design bending moment is 206.066 kilonewton per meter. Using this value, we'll be calculating the ultimate maximum bending moment in the next step. So to calculate the ultimate maximum bending moment, we refer to an Engg G of IS 456. So before that, we have to keep in mind that we always design or we always go for a balanced section if not given otherwise. So what do we mean by a balanced section? It simply means that the design bending moment, which we calculated in the previous slide, will be equal to the limiting bending moment. This limiting bending moment can be obtained from an Engg G, and the formula for the balanced section has been provided here. That is equal to 0.36 XU max by D bracket 1 minus 0.42 XU max by D into BD square FCK. So we'll be using this formula to calculate MU limiting. However, we do not know how to calculate this XU max. So we'll be referring to another clause of IS 456, that is clause 38.1. So it says that the limiting value of the depth of neutral axis for different grades of steel based on the assumption is that for different grades of steel, that is Fy is equal to 250, 415 or 500. In our case, we have Fy is equal to 415 here. So the value of XU max by D is equal to 0.48. So we can write for Fe 415, XU max by D is equal to 0.48. Please keep in mind that we always mention the clause which we are referring to in a subjective answer, whether it is your end semester exam or ES exam or any other competitive exam where you have to solve the question in a subjective pattern. So now substituting this value of 0.48 here in this formula given in Engg G, we obtain MU limiting as 0.138 FCK BD square. So this is the main formula. I've substituted the value of XU max by D from clause 38.1 and I've obtained the MU limiting value of 0.138 FCK BD square for Fe415. This is only for Fe415. So now substituting the values of FCK, B and D in this equation, we can obtain D required. So we have already assumed D equal to the effective depth equal to 510 millimeters, but we want to check that whether the assumed value is correct or not. So for that, we are using the help of this particular step in which we calculate a balanced section. We design a balanced section and we check that the load, the bending moment which is acting on our beam is sufficient, it has been sufficiently provided for by providing a sufficient amount of depth. So D required can be calculated from this formula and is equal to 498.873 mm. Now, because we had assumed the value of D to be equal to 510 mm, so we have provided a greater value. Required value is approximately 500, but we provided 10 mm extra. Therefore, we are safe. In case this value was greater than 510 mm, let's say this value came out to be 520, then we would have to redesign. We would have to go back to the first step and redesign the entire question up till here. So checks are very important in RCC and we have to see that every check is being satisfied. So moving on to the next step, we have to calculate the area of tension steel. To calculate the area of tension steel, we again go back to an Engg G, in which we have this formula XU by D is equal to 0.87 Fy AST upon 0.36 FCK BD. So from here we can calculate AST. Since we are assuming this to be a balanced section, we can write that XU is equal to XU max or XU limiting. And we can find the value of this XU max by D again from clause 38.1, which is equal to 0.48 for Fe415. So now we'll rearrange this formula to calculate the value of AST, which comes out to be 0.36 FCK BD upon 0.87 Fy whole divided by XU max by D. So substituting the values for FCK, Fy, B, D and XU max by D, we obtain the value of AST, which is equal to 1465 mm square. So the required value of tension steel, which is provided on the bottom part of the beam, is 1465 mm square. Now we cannot provide it in the form of area. We obviously provide steel in the form of bars. So we'll have to calculate or convert this value or area of steel into number of bars. So we assume that we'll provide 20 mm diameter bars. You can assume any valid value. It can be 16 mm, it can be 12 mm, whatever suits you. So just keep in mind that this value should not be very less or very high, and this will be requiring a lot of practice. So how do we calculate the number of bars? It is AST required upon area of 1 bar, which is calculated to be 4.67 bars. However, we can never provide the number of bars in decimal, and we cannot even reduce this value to 4. So we will always have to increase the value of number of bars to the next integer. Next integer in our case will be 5 bars. So we will be providing 5 20 mm diameter bars. So now when we increase, although 4.67 and 5 are very nearby, still we have increased the area of steel which we have provided. So we'll calculate this provided area of steel, which can be simply calculated by multiplying 5 into the area of a single bar. This calculates to be equal to 1570.79 mm square, whereas the required AST was 1465 mm square. We will require both these values in the future steps, so keep both these values handy. Now moving on to the next step, we will be calculating the minimum distance between individual bars. Now we can see we have provided 5 bars. There is a width of the beam which is equal to 200 mm, and we have provided some cover. So this cover is equal to whatever the value we assumed, that is 40 mm, and we have provided 1, 2, 3, 4, 5 bars. So now our aim is to calculate this spacing between the two bars. This is mainly provided, the spacing is required so that the aggregate, whenever we are pouring in concrete, the aggregate does not get stuck here. It is equally distributed throughout the beam. So the clause 26.3.2 of IS 456 tells us about the minimum distance between individual bars. So it says that this minimum distance should be equal to the diameter of the bar. If the diameters are equal, all these diameters are equal in our case, then it says that it will be the diameter of the largest bar in case we are using unequal diameters. Like example, we use these 3 to be 20 mm, these 4 to be 20 mm, and this one to be 12 mm. This is done when we are trying to design an economical section where we have to optimize the value of steel provided and steel required. So we can provide different diameters of bars, but for the sake of the question, we'll keep it simple and provide same diameter of the bars. And then the third part, it says that it should be 5 mm more than the nominal maximum size of coarse aggregate which we are providing. So all these values, we have to provide the greatest of all these. So we are calculating this space in between. So to calculate this space in between, we have to see that how many spaces are there. 1, 2, 3, and 4. So how do we divide this entire width of the beam? So we can say B minus 2 times of this cover, which is 40 mm, minus 4 times the diameter of the bar. That will give us the clear spacing between the bars. So we can simply write B minus 2Cn minus 4, 5. Here I'm writing 4, 5 because I have these 4 spaces available. 1, 2, 3, 4. You have to adjust this value according to the number of bars which you have been providing. So this is divided by 4. This will be the entire space, and because we have 4 spaces, so divided by 4. Now keep in mind that I have taken this value equal to 4 and not 5 because when we calculate Cn, it is till the middle of this bar. This is till the center of this extreme end bars. So we are eliminating this half a bar here, and including it in the value of Cn. Therefore, what we are left with is 3 whole bars here, half a bar here, half a bar here. So that gives us a value of 4. Keep that in mind. And we divided it by 4 because there are 4 spaces. So this clear space calculates to be equal to 35 mm. Now this value 35 mm is greater than 20 mm, which is the diameter of the bar, and it is also greater than the nominal size of the coarse aggregate, which is approximately 20 mm again plus 5 mm, 25 mm. So 35 mm is a safe clear space. So this arrangement of steel can be provided. If this was not satisfied, we would have to provide a different number of bars. We would have to change the size of the bar. We could take 25 mm diameter bar so that the spacing increases here, and it satisfies this clause 26.3.2. So moving on to the next step, we have to calculate the minimum reinforcement and the maximum reinforcement and check whether we have provided it according the provided reinforcement falls within the minimum and maximum value. So we need AST minimum to be less than AST provided and AST provided to be less than AST maximum. So we will be calculating AST minimum and AST maximum using clause 26.5.1.1 of IS 456. So AST minimum is given by the formula AST minimum upon BD is equal to 0.85 FY. Because we want to calculate the value of AST minimum, we can just cross multiply and calculate the value of AST minimum. 313.37 mm square. So this is the value of AST minimum. Now moving on to AST maximum. The maximum reinforcement which we can provide is the maximum area of tension reinforcement shall not exceed 0.04 BD, which is equal to 6600 mm square. So now we know that we have provided a value of 1570.79 mm square, which falls well within 313 and 6600. Because we have satisfied this condition, hence it is okay. So we can move on to the next step, which is calculating the shear. So as we calculated and checked the beam, was it safe for the provided bending moment? Similarly, we will have to check the beam for shear, that it does not fail in shear. So according to clause 22.6.2, we have to calculate the critical section for shear. So it says that the critical section for shear from this clause, it says that it is at a distance d, that is the effective depth of the beam from the face of the support. So clause 22.6.2.1. So how do we calculate this critical section, or how do we calculate the shear? This is a simple beam on which we have provided a UDL WU, and from this UDL we can calculate the load, the bending moment, and the shear also. This is the width of the support which has been provided, and we have reactions R at the center of the support. So now from the face of the support, you can see that this is the face of the support. We have to move a distance d towards the center, and this will give me the section XX, which is the critical section for shear as per clause 22.6.2. So when we are checking for shear, we have to carry out multiple calculations to first calculate the design or the factored shear force, and then calculate this factored shear force at the critical section. So let's do that. So first we'll calculate the factored shear force at the center of the support at this location. So center of the support, VUS is equal to WU into L effective by 2, or WL by 2. So this calculates to be equal to 1555 to 1.875 Newton, or 155.5 kilonewton. So this is the value here. Now we have to calculate this value of shear at the critical section. So we can simply assume or calculate it using similar triangles ABO and CDO. So from similar triangles we have AB upon BO is equal to CD upon DO. So we need to calculate this value of CD, but we do not have this value of DO yet. So first we'll have to calculate this value X. So to calculate this value, we can simply use the logic. This distance is X. We know L effective from the center of the support till the center is the length is L effective by 2. We know the width of the support. We know that this portion is distance d as per the previous clause which we studied. So we can simply write X is equal to L effective minus WS by 2 minus d by 2, where WS is the width of the support. Because this is from the center, we will take half the width of the support. So X calculates to be equal to 1.99 meters. Keep in mind that we have to take this value of width of support and d in meters, because L effective is in meters. Now from similar triangles, we have this equation. We can compute the value of VUC, which calculates to be equal to 116,788.125 Newton, which can be written as 116.78 kilonewton. So we can entirely skip this calculation of shear force at the critical section if we are running out of time in the exam, but it is always preferred because it will cost you a few marks if you don't carry out this step. Now that we've calculated the value of shear force at the critical section, we can calculate the nominal shear stress using clause 40.1. It says that tau V, that is nominal shear stress, is equal to VU upon BD. This is not D in the subscript, but this is D. So you can write it like this. And we have the value of VUC, we have the value of BD. We can calculate tau V, which is equal to 0.76 Newton per mm square. So this is the value of nominal shear stress which the beam will experience. We have to check this for maximum shear stress, that is tau C max. What is tau C max? Tau C max is the maximum shear stress which concrete can take. So for M20 concrete, the value of tau C max is 2.8. So we need tau C max to be greater than tau V. That is that the actual shear stress which is acting on the beam, which is tau V, should be less than the maximum value which concrete can take for this particular case. So 2.8 is obviously greater than 0.763, hence it is okay. And we can move on to the design of shear strength of concrete, provide the shear reinforcement. So we'll be using table 19 for this calculation. In this, we have to calculate the percentage of area of steel provided, which can be calculated from 100 into AST provided upon BD. So AST provided we can obtain from the previous steps, which is equal to 1570.79. So this percentage calculates to be equal to 1.026%. Now, if we refer to this table, what we are getting is design shear strength of concrete, that is tau C. So tau C simply means that what amount of shear will be resisted by concrete, and then which cannot be resisted by concrete. For that we will be providing shear reinforcement. So we have provided an AST value of 1% approximately, and we are using M20 grade of concrete. So for 1% of steel, the tau C value is 0.62. However, keep in mind that because this value is very close to 1%, so I have taken the value equal to 0.62. But if you take this value, if this value was somewhere like 1.1 or 1.12, then we would have to interpolate. So just for the sake of the question, I have interpolated this value and obtained tau C corresponding to AST equal to 1.026%, and it calculates to be equal to 0.6252 Newton per mm square. This tau C is the value of shear which the concrete will resist. We had the entire value of nominal shear stress equal to 0.763 Newton per mm square. Now the entire value of shear which is going to act on our beam is 0.763, and how much can concrete resist? It can resist only 0.6252 Newton per mm square. So now, because this value of tau V is greater than tau C, we have to provide shear reinforcement. Had this value of tau V been less than tau C, say it was 0.5, so there was no need to provide shear reinforcement because concrete would have provided the resistance for shear. However, in that case also we provide a minimum shear reinforcement which is necessary. So now we will be designing the shear reinforcement required in the next step. The shear reinforcement required can be calculated from clause 40.4, which says that VU minus tau C BD is the shear reinforcement which we have to calculate. So we will be providing shear reinforcement only for the balance part. Tau US is equal to tau V minus tau C. So tau V is 0.763 minus 0.6252. So this approximately calculates to be equal to 0.13 Newton per mm square. So for this amount of shear stress, we will have to provide shear reinforcement using this formula. Shear stress is equal to shear force upon area, or we can say shear force is equal to shear stress into area. Since this formula is in the terms of shear force, we will have to convert this design shear stress into shear force, which is VUS is equal to tau US into BD, which calculates to be equal to 19.89 kilonewton. So substituting this value here in this equation of clause 40.4, we can calculate this shear steel, the required shear steel or area of shear steel. Or what we can do is instead of calculating ASV, we can assume this value of ASV and calculate SV. SV is the spacing between the stirrups. So what are stirrups? Stirrups are the shear reinforcement which we provide. In this case, we will be providing vertical stirrups of 8 mm and it will be two-legged. So for that, the ASV will be equal to twice of pi by 4 into 8 square, which is equal to 100.53 mm square. Now we can calculate the spacing. So using this clause 40.4, we rearrange and we calculate this value of SV, which is equal to 930.68 mm. However, this is a very big value, and as per clause 26.5.1.6, the minimum shear reinforcement has to be equal to ASV upon BSV should be greater than equal to 0.4 upon 0.87 Fy. So from here we will calculate this value of maximum spacing. So rearranging this equation, we get ASV minimum into 0.87 Fy upon 0.4 B. But ASV we are taking to be equal to 100.53 corresponding to the 8 mm diameter bar, two-legged 8 mm diameter bar. So SV max calculates to be equal to 302.469 mm. So the maximum spacing which we can provide between the stirrups as per clause 26.5.1.6 is 302.469. We cannot go beyond that. And we have obtained a spacing of 930.68. So this is not possible. So now we will be checking clause 26.5.1.5 for maximum spacing. Since we have decided the diameter of the bar and we've decided that we will be providing two legs in the stirrup, now we have to decide the spacing. And according to this clause, the spacing shall not exceed 0.75 D. For vertical stirrups, and we are using vertical stirrups, it should not be exceeding 300 mm and it should not be exceeding the value calculated under clause 26.5.1.6. So we can write it in this form and calculate individually. So 0.75D calculates to be equal to 382.5 mm. The next is 300 mm, and from clause 26.5.1.6 we have 302.47 mm. So we will take the least value and maximum SV will be equal to 300 less than equal to 300 mm. So the maximum spacing which we can provide between our stirrups is 300 mm. Therefore, we will be providing 8 mm diameter two-leg vertical stirrups at the rate 300 mm center to center throughout the length of the beam. So we will not be changing the spacing throughout the length of the beam and keep it constant at 300 mm. Now we have to provide or we have to check the development length, which will be covered in a separate video on development length for this question as well, and we'll be calculating the values there. Moving on, we will calculate deflection. We refer to clause 23.2 of the code. So how do we check for deflection? The L effective upon D ratio, the maximum ratio should be less than L effective upon D ratio, which has been provided in the question or provided by us. So how do we obtain this maximum value? To obtain this maximum value, we have to refer to clause 23.2.1. So in our case, the beam is simply supported, for which the value has been provided as 20. This is for spans up to 10 meters. Since our span is less than 10 meters, so we will be taking this value. For simply supported, the value is 20. Now, what is the formula? The formula is simple. L effective upon D. The maximum value will be equal to 20, which we have obtained from here, into KT, KC, and KF. So what are these KT, KC, and KF? KT is the modification factor for tension reinforcement. The tension reinforcement which we have provided, we will introduce a modification factor because it will affect the deflection. We can obtain this from figure 4 of the code. Then KC is modification factor for compression reinforcement. Again, when we provide the compression reinforcement, it will affect the maximum value of deflection or L effective upon D. This can be obtained from figure 5 of the code. In this particular question, since we have not provided any compression reinforcement, so the value of Kc will be equal to 1. So I can simply write Kc is equal to 1. Now, last is Kf. Kf is the modification factor for flange section. This is used for T-beams or flanged beams if we are considering that, and can be obtained from figure 6. Since in the particular question, the beam is rectangular, so Kf is equal to 1. So now the value of Kf will be equal to 1. So we can compute L effective upon D max is equal to 20 into KT. Now the question reduces to obtaining KT from figure 4. Now coming to figure 4 of the code, it says that Fs is equal to 0.58 Fy, area of cross section of steel required upon area of cross section of steel provided. So from this we obtain the value of Fs is equal to 224.5 Newton per mm square, as we knew the values of area of steel required and area of steel provided by us in the question. What do we have to do now? We have to calculate the modification factor K. So when we are KT, so when we are calculating this, consider this figure. This figure gives us the modification factor on the y-axis and the percentage tension reinforcement on the x-axis. In the previous steps, we had calculated the percentage of steel provided using the formula 100 AST upon BD. So we can simply use the same value, which is 1.0266. We can approximate this value equal to 1.03. Now, if we see this figure or this graph, we can see that 1 is here, somewhere here, and the value of Fs is 224.5, or we can simply say 225. Now, these lines are representing the values of Fs. We fall somewhere between Fs is equal to 190 and Fs is equal to 240. So, drawing a line corresponding to 1.03 or just 1, somewhere here the line Fs for 225 will lie. So when we see the corresponding value of the modification factor is approximately equal to 1. Because this is the only figure from which we can calculate the modification factor, we have to carry out to some extent approximation, because this is a very relative value. The point is very relative. So keeping it easy, we assume that from this figure we have obtained KT equal to 1. So now we can simply write that KT is also equal to 1. So L effective by D, the maximum value will be equal to 20. Next is L effective by D provided, which is equal to 5300 upon 510, which is equal to 10.392. So L effective by D maximum is greater than L effective by D provided, because 20 is greater than 10.4. Hence, this is okay. The maximum deflection which was allowed is 20 mm, but we have experienced 10.4, the ratio, I mean. So since it is within limits, hence this is okay, and we can move on to the detailing. When we look at the detailing, we have to provide the entire cross section which we have designed, the dimension, the overall depth, the effective depth, the number of bars, the clear spacing between the bars. We have to mention the number of bars, 5 20 mm diameter bars, the clear cover, the stirrups which we have provided along with the spacing. We can draw them alongside so that it can be marked in just one figure. And these are the anchor bars. In some cases, these might be the compression bars when we move on to doubly reinforced beams, but here, because it is a singly reinforced beam, these are anchor bars which are provided to keep the stirrup in place, and also for safety purposes. Keep in mind that the stirrup is bent at a 180-degree hook, and it is always provided towards the compression side. You will never provide the hook on the tension side. It has to be, this is wrong. You have to provide the hook on the compression side. And here we can see the longitudinal section, the L section of the beam, in which at 300 mm the stirrups have been shown throughout the section. The support has been shown, the hook has been shown, and the anchor bars have been shown. So this is the detailing and is the last step of the design, and this is very important. So in this video, we cover design of a simply supported singly reinforced beam, a numerical problem on it. So thank you.
Hello everyone. In this part of the video, we are going to see how to model a beam in Revit, how to add rebars to the beam, and also how to do the drawings for the beam and reinforcements. So the first step what we need to do is to model the beam. And from our structural input, as you can see here, the clear span of the beam is 5 meters. So what you see in the screen is two columns that has been already placed in the exact distance that we want. If I go to the plan view and measure the distance, the clear span between the columns, you can see that it is exactly at 5 meters. So this is set. Now all we have to do is model the beam. So to model the beam, all you have to do is go on to structure and click on beam. But if I go to the 3D view, you'll notice that the columns are starting from level 1 and going until level 2. Therefore, our beams have to be at level 2. So I had to go to the level 2 view and start modeling my beam here. Now I can go to structures, click on beam, and then I can start modeling. When it comes to modeling a beam, first thing you need to do is specify the beam type. As you can see here, I already have a beam with the exact same size as per our structural instructions. It is 300 by 550 mm, 300 mm wide, 550 mm deep. How do I know this? The name says it. In addition to that, if I click on edit type, you'll see that there are two parameters. These parameters may have different names for different families, but almost all columns, rectangular beams will have a breadth value or a width value and a depth value. In this case, the width is 300 mm and the depth is 550 mm. If you want to change that, you can duplicate it and then give it a different dimensions. Okay, right. So now we have the correct beam type. The next step is to start modeling it. To model a beam, you'll need to define the start point of the beam and the end point. In our case, although I said the beam will be spanning between the edge of this column and edge of this column, in reality, if you look at it from an analytical perspective, the analytical line of the column and the analytical line of the beam has to meet at the same point. Therefore, you'll have to start the beam from the intersection or the center point of the column, which also happens to be the intersection point of these two grids. So I'll start my beam from here, and then the end point of the beam will be the intersection point of the other grid or the center point of the other column. Once I click here, you'll see the beam coming. But also something you need to notice is that although I picked this as the start point, the actual beam, the geometry part, is actually starting from the face of this column. The reason is Revit recognizes that, okay, this is a beam that is spanning between these two columns. So although the analytical point starts here, the geometry part will be cut automatically by Revit in order to place the beam exactly between the columns. You can see it in the 3D view as well. Now we have the beam ready. The next step is to start modeling the reinforcements. So to start modeling the reinforcements and to make it easy for you to understand, what I am going to do is I am going to create a couple of section views for the same beam. The first section I'm going to create, first of all, to create a section view, there are two ways. One, you can click on this button here directly, or go on to the view tab and then click on section here. Either way works fine. Both are exactly the same thing. Now, first I'll draw a section in this direction, and then I'll modify the far clip. Then I'll create one more section which will act as the cross section view for the beam. Done. So now I have two views and I'll be able to find those two views in the section view. So let's open those two views. There's section 1 here, which will be the longitudinal view, and then there is section 2, which will be the cross sectional view. Now we'll be modeling our beams from this cross sectional view. Although we are going to model our reinforcements from this cross sectional view, we will have other views open on the side to help us get a better context. First, I'll remove level 1. I don't want that because the beam itself is in level 2. And then let's reduce the size of the project browser and the properties tab. Now I can press WT. What it will do is it will open all the tabs in windowed mode. So it will make each tab into a different window. This will help us have multiple views opened simultaneously. Now this is the view I'm going to use. So I'll make these ones moved here. And this is the section I'm going to use. So this is the beam that we're going to detail. And this is the section box or the crop view, not the section box, but the crop view. So we'll reduce the size of the crop view to show only the part of the beam that we want. And we'll reduce the grids and the columns. We'll reduce the extent of the grids and the levels to our expectations. Next, as you can see, relative to the size of the beam itself, the grid head and the level heads are very big. This is because of the scale. This is a very small drawing which is just showing a cross section of a single beam. To accommodate this, let's change the scale to something smaller. Let's make it 1 to 20. Now it looks more appropriate. Let's switch the section heads. In fact, we can go ahead and turn off the sections altogether. We do not need this section here. To hide a section, press VG to go into the visual graphic settings, go into annotations, and then turn off sections. Done. Now we have the view according to our need. The next step is to turn off this crop view. So we'll talk. The next step is to turn off this crop region. So we'll come here and turn off this crop region box. That will hide the crop region. And further, what we are going to do now is we are going to turn off this pattern of this beam. This pattern is coming from the material. In order to hide this pattern, we can go to again the visibility graphic settings, scroll down to structural framing, under cut patterns, override and hide both the patterns. That will remove the pattern. Great. Now we can go ahead and model our reinforcements, and we'll be able to see them here in the plan view and in the 3D view as well. Right. So the first step of modeling reinforcement includes selecting the host. In our case, the rebars are going to have the beam as the host. So we'll select the beam and then click on rebar button here. Once you click that, the first time you'll be getting this window. You can ignore that and click OK. After that, you will be prompted with choosing a rebar shape. In Revit, each rebar shape will have a different number, and this number can differ between project templates. In the default Revit template, these are the numbers assigned to the shapes. Straight bars are called 0, and L bars are 11, U bars are 21, and stirrups are 52. There they are. So similarly, each different unique shapes will have their own number. If you look at our structural input on the screen, you'll notice that the beam has 2 straight bars on the top and 5 straight bars at the bottom. So we are going to use the straight bars for these bars. And then for stirrups, we are going to use shape 52. We'll come to that later. For now, for the straight bars, we'll use shape 0. Done. Once you select that, you can come to the view you are going to place the bars in. And if you come inside the beam, you'll notice that there is a green line boundary showing the cover and also a dot representing the bar. Okay, this will be the bar that you're going to place. You'll have to decide where you're going to place. Okay, within the beam. If you go outside, you won't be able to place it. So within the beam, inside the cover, you'll have to decide where to place it. And something about cover, we'll talk about it later. But you won't be able to place outside the cover as well. You will have to place the bars inside the cover only. Okay. Now, after selecting the shape, the first thing you need to choose is the placement plane. In this case, it is correct, but there are multiple ways of choosing the placement plane. But what is a placement plane? If we look at this window, let me go back. If you look at this window, this plane is coming from this section. Sorry, this view is coming from this section. And this line you see here as a plane. This is the active work plane of this view. And we need our straight bars to go through this view, through this beam, correct? If assuming this view to be in YZ plane, we want our bars to go through XZ plane, right? So the bars has to go perpendicular to our active work plane. Therefore, after selecting rebar and the right shapes, the placement plane, you will have to select it as perpendicular. In our case, it is already in perpendicular. If not, it will be probably in parallel. If you have it in parallel, what you'll notice is you'll see that the bar is actually placed parallel to the work plane. This is not how we want the straight bars to be. Our straight bars has to go perpendicular to this direction. So we'll choose the placement plane as perpendicular to cover. And now you'll notice the bar is going perpendicular to the plane. Right. So that is sorted. The next step is, if you look at again the inputs, you'll notice that it is not a single bar that we have to place. We'll have to place 2 bars at the top and 5 bars at the bottom. Now, you can think of it this way. Place 1 bar, 2 bar, 3, 4, and 5. So this is one way of modeling, which is not the right way as well, because it is not that effective. So let's undo the changes. The right way to model this, right way to model a fixed number of bars is changing the bar set. This is a single bar. We will have to make it into a set of bars. And the way we define the number of sets or the spacing between bars, you can change them from this tab called rebar set. And by default, the layout says single. Quantity and spacing is grayed out. What we want is we need to change this into something else. Let's see what are the available options. If you open this, you'll notice that there are multiple options. What we'll focus on is fixed number and maximum spacing. If the input of your bar is based on a fixed number, we'll use fixed number. If your input says the number of bars in terms of spacing, we'll use fixed spacing. For example, the main bars in our input says either 2 bars or 5 bars for the main bars. But for stirrups, it does not mention how many bars has to be placed. Rather, it is mentioning the spacing between each adjacent bar. So for the stirrups, we'll be using maximum spacing. For the main bars, we'll be using fixed numbers. In our case, we are modeling the straight bars, so we'll use the fixed number option. Then quantity gets enabled. Now we can decide the number of bars we want. So we are going to model the bottom bars first. So we'll say 5. We want 5 bars at the bottom. Right. Before placing, there is one final thing that you need to change, and that is the diameter of the bar. We'll have to place a specific diameter of bar, correct? According to our input, the diameter of our bar is 20 mm. So we'll have to make sure that these bars are 20 mm in diameter. So where do you control the diameter? The diameter of the bar is based on the type, the family type. So for each element, every element in Revit, we'll see the type here. And as you can see, it shows H8. Again, this is from the Autodesk default template. Each template has different namings for their rebars. In this case, it has been called H. If I open this, you'll see the other available rebar types. One of them is H20, which is representing 20 mm bar. So we'll use that bar to place our 20 mm bars. And now if you come back to the beam again, you'll see the bars have gotten bigger. And the number is 5. And now I can place it exactly on the curve. Right. So one part is done. I have 5 numbers of 20 mm bars placed at the bottom. The next step, placing the top bars. To place the top bars, the only difference between this setup, as you can see, again, it is still in 5 numbers of bars. We have to change it to 2. So we will go on to rebar set, change 5 to 2. And now you'll see that the count is 2. So now I can place it exactly on the curve. Okay, done. Now I have the main bars and main bars both top and bottom placed. But if you notice, it is not yet visible in the plan view nor in the 3D view. If you click on the beam though, then you are able to see the reinforcements inside. But before, without clicking the beam, it is not possible to see the reinforcements. To change this behavior, you need to change a setting. Basically, what is happening now is the beams are actually hiding or obstructing the view of the rebars because the rebars are inside the beams. To change this behavior, we'll need to select all the beams, all the reinforcement bars. And then these bars have a parameter here called, say, visibility states. Click on it. And then here you can say in which views do you want the rebars to be unobstructed. So in our case, it is the 3D view. Find the 3D view here. There it is. And then in level 2 plan. So level 2 plan is here. So in these two views, although the rebar is inside the element, it will still be visible because we have override the default settings and we have asked Revit to show them unobscured. If I click OK, now you'll see the bars in the view even without clicking anything. Okay. The next thing you can notice here is, here you'll see that the bars have an actual thickness, the diameter 20 mm. But in the 3D view, you'll notice that it is not the case. It is a very thin line. It is not showing the diameter. This is the default behavior of Revit when you have the detail level as medium or in coarse. If you want to see the actual shape of the rebar, you will have to change the detail level to fine. And now you will be able to see the rebars. Okay. That's it. So now we are able to see the bars and we have placed the main bars as well. Right. Next step is to model the stirrups. Let's make 3D view bigger. The next step is to model the stirrups. To model the stirrups, it is the exact same procedure. The only thing you'll have to change is, I'll show you which are the changes. So we'll select the host, which is the beam, then click on rebar. First thing you need to change is the shape, obviously. It is no longer a straight bar that we'll use for stirrups. It will be an actual stirrup bar, a hook. a stirrup with a hook. So we'll scroll down to shape number 52. And there are two shapes as well. There is 51 which also looks like a stirrup but does not have a hook. We need our stirrups has to have a hook. So we'll choose 52. Then the next thing is, if you come here and place, you'll notice that the bar is not looking right. The reason is the main bars, those were going perpendicular to this view. So we had the placement plane as, oops, give me 1 second. The placement plane as perpendicular because the bars were supposed to go through the beam. In this case, the bars are supposed to be placed parallel to the plane. The stirrups do not have to go perpendicular to this plane. It has to be parallel. So we'll change it back to parallel. And now if I come and try to place it, you'll see it is being placed in the right plane. Although the size is very big, the bend diameters are big, we'll change that. But you'll notice that the bars are being placed in the correct plane. So now the placement plane is sorted. Next step, let's change the diameter of the bar. It has to be not 20 mm. According to our input, our stirrups are supposed to be 8 mm bars. So we'll say 8. And now you'll see that it is in the right orientation. Now if I try placing it, first of all you'll notice that the stirrup is extending to match with the cover. But you'll notice the main bars are already near the cover. So the main bars has to be pulled inside the stirrup. But Revit will do this job for us. You don't have to worry about it. As soon as you place the stirrup, Revit will pull those main bars inside the stirrup to make space for the stirrup. Okay, so Revit is smart enough to understand that this is the stirrup and the main bars has to go inside the stirrup, so it will pull them inside. Okay, but it looks like we have placed the stirrup and everything seems right. But if you look at the 3D view, you're not able to see it first of all. So we'll select the stirrup, change the visibility states to be unobscured in the 3D view. There you go. Now you'll notice that there are only two stirrups. There is one here. Let's make it bigger or wide. There is one bar here and then there is another bar at the end. The reason is the way you place the bars. While we were placing the main bars, we had the rebar set as fixed number and the quantity as 2. We haven't changed it yet. So the stirrups are also being placed with the same layout. We need to change that. Instead of placing it with a fixed number, according to our input, you'll notice that the rebars for the stirrups are being defined, the quantity is being defined in terms of spacing. So we'll say maximum spacing and change the spacing to 300 mm according to the input. Now if you come back to the 3D view, you'll notice that there are multiple rebars. You can see here as well. As soon as you change to maximum spacing, quantity was disabled and spacing was enabled. So now when you set the spacing, the quantity will be automatically calculated based on the length of the host. So our host is this. So our rebars are trying to fill the space with the space of 300 mm. And in order to fill the space with the rebars of 300 mm spacing, it needs 18 bars. So that calculation will be done by Revit automatically. Okay. So now we have the main bars, both top and bottom, and the stirrups as well. Before we move on to the documentation part, we have to look at one more thing. When I select the host and click on rebar and try to place it, I told you that these green lines represent the cover thickness. But what is this thickness? We haven't set any specific thickness for it, the cover depth. According to our input, it is 40 mm. So how to specify the 40 mm cover? In Revit, the cover is not something that is specific to the rebar element, but it is a part of the host element. So we will have to select the host, the beam, and then change the cover. So how to do that? After selecting the host, come to the properties tab. Here you will see rebar cover. There are 3 covers: top face, bottom face, and other faces, meaning the side faces. And they are having a drop down. So these are all the available cover options that this model has. To add a new cover, let's say we don't understand what this means. They're having 50, 45, 40, something like that. But let's say we want to create a new cover thickness. In such a case, what we need to do is go into structure, under reinforcement, click on this small arrow here and click on rebar cover settings. Once you open that, here you'll see all the available options. To add a new rebar cover, you can click on add, you see here, and here you can rename it to something else. Let's say beam cover 40 mm and change the actual value also to 40. Okay, I have already created something like this, beam 40 mm, so I'm going to use that. Okay, click cancel. Now I'll select the beam, rebar cover top face, go to the top, beam 40 mm, do the same for the other covers as well. So you'll be able to create different covers for the top face, bottom face, and side face as well. In our case, we'll keep things simple and use the same cover all over the sides. Now we have the cover setup, and as you can see, the bars moved inside because the cover changed from 20 to 40. Okay, so now the cover is 40 mm. Now let's move ahead to actually annotating this view. So the first step we'll do is we'll add the dimensions. So this will be the depth, this will be the width. Now we know the beam dimensions. Next step, we'll have to annotate the rebars. Next, to tag the reinforcements, you can go on to annotations and click on tag by category, or again press TG. Next, I can start tagging the rebars by clicking on the bars themselves. So as I click on the hover over the bars, you'll see the tags coming up. So we'll first select the top two bars and click. There I have a tag that says 2T20, representing two numbers of 20 mm bars. Similarly, I'll tag the bottom bars as well. Now it says 5T20, representing 5 numbers of 20 mm bars. Next, we'll tag this stirrups. If I try to tag the stirrups, you'll see that it is still showing 18T8, meaning 18 numbers of 8 mm bars. But this is not how we represent stirrups. We'll have to represent the stirrups by their size and their spacing. So we'll have to use a different tag family. So we'll select this tag and change it to, instead of quantity and size, we'll say size and spacing. So once you click on it, you'll see that it shows 8 at 300 cc, center to center. So this means 8 mm bars spaced at a spacing of 300 mm. Okay. So now this drawing represents the section view of the reinforcement for this beam. Let's adjust the scale and other options. Done. Okay. So this section drawing is ready. Next, we'll move on to the longitudinal section and see what is happening there. If you move to section 1, first of all, we don't need the columns in view. So we'll reduce the crop view. And again, we'll change the scale as well to 120. Adjust the levels and the grids. Right. Now we'll do the same changes that we made in the cross sections. First, we had to reduce the hide the pattern. So we'll go to VG settings, structural framings, and this time it will be the surface patterns, not the cut patterns. So I click on override and hide the patterns. This will be for beams. Since columns are also visible here, we'll do the same for columns as well. Columns, hide. Hiding these patterns is more of a personal preference. Since we are going to detail the rebars, having the patterns is unnecessary and may clutter the image. So it is preferred to hide them. And we'll hide the section view also. We don't need them. Annotation and sections. There you go. Okay. So now let's try to annotate this view. We'll first hide the crop region. Done. We'll show a dimension representing the clear span, which is 5000 mm, which is exactly what we want. Good. Next, we'll add tags here as well. So TG, and we'll start with the main bars. Let's tag it here. So it says 2T20. Good. Tag one more at the bottom. This one shows 5T20. So this is a tag representing the top bars, and this is a tag representing the bottom bars. Next step is to tag the stirrups. To do that, again press TG and click on the stirrups. Let's tag it here. Let's pull it out. Okay. Let's remove this. Tag it again. This time with free end. Free end allows you to place the tag wherever you want. Done. Now again we'll change the type to show, instead of quantity and size, it should show size and spacing. Okay. So now we have a tag that is representing the stirrups as well. Next step, if you look at the inputs, you'll notice that the bars have a hook, the bottom bars specifically. There is a hook that is going up. But this bar that we have in our model does not have that. So how to add a hook to our model. Click on the rebar. One of the properties you see here is about hooks. And the exact name of the parameter is hook at start and hook at end. So assume this to be a start and this to be the end. There are two ends to a rebar. You can add hooks to both of them. So let's add a hook to the start, and the hook bend angle can also be specified. According to our input, we need a 90-degree hook. So we'll say standard 90-degree. And the same for the end as well. Standard, okay, sorry. Hook at start, hook at end. 90 degrees. Apply, and there you go, you have a hook. Okay. But what is this hook's length? That is something that you'll have to change in the type parameter. Click on the type, and you can see there is a button called edit next to hook lengths. Click on it, and here you'll see what is the name of the hook and what is the hook length. By default, it will be auto calculated based on the diameter of the bar. If you don't want that, if you want to manually change it, you can uncheck this and give it your own number. Oops, sorry. Uncheck this and change this to a different number. You can reduce it or you can increase it. For now, I'll leave it at auto calculate. So now we have a hook. So our section view is also almost ready. One thing that is pending is this gap here. It is looking ugly because the view got cut based on our crop region. So what we can do is we'll add a break line here. To add a break line, you can go to annotate and click on detail lines, or where is it, components. There. And I have a break line family here. If you don't have this break line, go to insert, click on load Autodesk family. From here you can search for whatever family you want. Just search for break line. I think it should be two different words. There, detail item, break line. Click on it, load it, and then if you come back to annotate and click on component, you'll see the type here. Next, we can place it. So I'll place it like this. So this is going up, it should go down actually. And then I will extend it. Next, I will copy this from here to the other side as well. And now there is a clean cut. Okay, so now it looks more neat. So this is the bare minimum that we'll have to add to detail a bar and a beam. The next step after this is basically to populate a sheet with all these views that we have. First of all, we'll go to the plan as well and see what can be done here. We do not want to see the bars in the plan view in full length or full thickness, so we'll change it to coarse. Okay, this should be enough here. And we'll have the sections invisible, and the columns have been tagged, but the beam is not tagged yet, so we'll tag the beam here. TG beam size has been shown here. If you want, you can add the dimension as well between the grids. It is preferable to show the dimension between the grids wherever the grids are visible. Done. Next, we'll create a new sheet. We'll choose a template for it. There you go. And now we'll have to place the views that we created into the sheet. So what are the views we are going to use? We'll first use the plan view. And we'll place it somewhere here like this. And if we zoom in, you'll see the bars also shown. And yeah, it shows the plan name as well. Next up, we'll use the sections. So there's the cross section and the longitudinal section. So we'll use section 1, which will be the longitudinal section, and place it. Try to place the views with the grids aligned, and actually Revit will help you do that. Just drag and drop, and when you come closer to the, when the views are aligned, you notice there's light blue line coming up. So that means you are perfectly aligned. With that help, you can place the section view as well. So now we have the section view and the plan view. We'll move them down. Next, right next to the longitudinal section, we'll place the cross section. So we'll pick section 2, drag and drop. There you go. Okay. So now we have the section view and the section view in both directions and the plan view. You can leave this as it is, or if you find it to be too small, you can click on it and change the scale to 1 to 10. This will make it a little bit bigger. I personally prefer this, so I'll make it 1:10. Let's modify this and arrange it again once again. Just because we changed the scale, the text have been moved all over the place. There you go. So now we have a view with the plan, the sections in both directions, and that completes our beam modeling and reinforcement modeling for the beam. Now this drawing is ready for exporting. But before this, just for additional context, if you want, you can place the 3D view also here to give the person who's reading the drawing a better context about how to see the drawing. For that, what we're going to do is we'll go to 3D view and we'll select all the beam, all the reinforcements, isolate them, click OK, and then we'll press HI. That will isolate only the beams, and we'll move to an isometric view like this, something like this. Yeah. Once you're done with this, select this button and say save orientation and lock view. This will lock the view, so we say 3D reinforcement. Now you won't be able to rotate it. See, you won't be able to rotate it. Next up, go to the same sheet, find the 3D view you created, drag and drop. It is very small because it is at 1:100. Change it to 20, apply. Okay, this is too big. Let's try changing it to 1:50. Okay, this is much better. Okay, so now we have a 3D model of the reinforcements, 2 cross sections and a plan. So this completes our modeling procedure. Before you print, you'll have to change the sheet name and sheet numbers. So open the project browser, find the sheet, right click, rename, and we'll give a number, let's say it's 101, and we'll call it beam reinforcement. Good enough. Okay, and you'll see the name and the numbers here is 101 beam reinforcement. Now you can go ahead and print it. So to print, either click this button or go to File, Export, and then click on PDF. Choose the location where you want to place it, and then choose the paper size. Let's use, this was a title block of A1 size, remember? So we'll use A1. File, Export, PDF. Page size will be A1. We'll say fit to page, and then we'll use vector processing in color, and then click Export. Still no. Once you do that, the file will be saved. You can go to the folder, open it, and you'll see the file being created. So this is the final drawing that you will be publishing. Okay. So thank you for watching. That is all we had for in this session. We learned about how to create a 3D model of a beam and add reinforcements to it, and also add drawings for it. See you all sometime later. Thank you.